Hello, Calculus 1. Here's our formulas for section 5.8. We're trying to do these integrals that result in arcsine, arctangent, arcsecant. So it's these patterns of these three integrals. Three integration patterns, three formulas. So we're not integrating arcsine, arctangent, or arccosecant. We're not integrating those functions. We're integrating these functions that result in these. So we can't integrate those functions until chapter 8. We can learn a technique. Cal 2 is some more advanced integration techniques, a lot of things, but we do a lot more integration, a lot more applications of integration. So far you think that if I'm doing an integral, you know what it kind of means. If I wanted to apply it to something, you would say I'm finding the area under a curve, maybe. Again, in Cal 2 we learn a lot of other applications for integration, so that'll be awesome. But you're right, so look at this problem. I made up this problem. An integral from -2 to 2, 4 over x squared plus 4. It's kind of a classic. And so not all these functions have very interesting shapes. I think this one does, though. I think this one has this kind of funny bell-shaped curve a little bit. It's not the bell-shaped curve, but it's this shape. And apparently, I'm graphing this function. When x is 0, I'm at 1. So there it is. This is a picture of it. It's not to scale, I guess. And then I'm integrating from -2 to 2. So I could interpret this problem as finding this area, But anyway, let's just do it. To do it, I have to recognize how to integrate this. It's not U substitution, really. It's not a natural log. Some people think anything in the denominator is a natural log. That's not what this is. This is a good old arctangent. I can see it very clearly. There's a 4 out front. I'm going to pull the 4 out front. And then it's 1 over a. Maybe you've identified the a as a 2. 1 over a arctangent u over a. By the way, the u is just an x. And so there's nothing. The du is just dx. Very simple little problem. So I get x over 2. I don't put a plus c. Now I have this definite integral from -2 to 2. So here I go. I've got this 2 out front. And I have the arctangent of, when I plug in a 2, that's a 1. Here comes the train. I have to talk louder for the train. Minus, there's a 2, and an arctangent of, when I plug in the -2, that's a -1. So, sometimes arctangents are weak, arcsine, all these things are little weak areas for students sometimes. Your calculator will help. But it turns out, the arctangent of 1, it helps to know what it is. It's the angle whose tangent is 1. And the angle whose tangent is 1 is 45 degrees. I should talk in radians, though, in this problem. So that's a pi over 4. The angle whose tangent is 1 is pi over 4 times 2 minus 2 times the angle whose tangent is -1. And that would be an angle in quadrant 4. That would be -pi over 4. That's his name. There's some stuff going on here about the restricted range of these arc-trig functions. So arctangent is restricted to answers that are in quadrants 1 or 4, or answers between, positive pi over 2 and -pi over 2. So if I answered 45 degrees in quadrant 1 for that answer, and -45 degrees in quadrant 4 for that answer. And that's the appropriate answer, pi over 4 and -pi over 4. Your calculator would tell you that. Anyway, check this out. That's a pi over 2 when you multiply by 2. That's a positive pi over 2 when you multiply by 2. And when you add those up, the answer is pi. That is so awesome. The area that we shaded here has an area of pi. I love problems like that. So that's cool. That was a nice application of a definite integral of an area problem involving these. There's more to say here in section 5.8, a little more complicated problem. Sometimes you have to complete the square. So I'm going to erase this, get rid of this example. This is a classic problem. I'm just making this up. It's a little dangerous here. X squared plus 12x plus 40. I'm sorry, let's just put a 3 on top for fun there. Sorry, I'm sorry. All right, here we go. This is a nice problem. So you might not think that. Look, you're trying to look at this. You're trying to understand, is this one of these patterns? Is this one of these new problems? And it sure doesn't look like it. But you know what I want is a quantity squared plus a number squared. I want some kind of quantity u squared plus an a squared. You know, I kind of have that, except I have this middle term here, which is not in the formula. So again, I said you could complete the square. So I'm kind of going off to my scrap paper here, and the way you complete the square is this. This is an old algebra technique. I kind of shove the 40 out here, and what I do is I add the appropriate number here. So it's always, to complete this square, make it a perfect square trinomial. It's half of this, which is a 6. Squared is a 36. I wish I had a 36. I'm going to add 36. Then I'm going to, I can't just add 36 unless I come over here and I subtract a 36. So what I have is a perfect completed square, and I manipulated legally to get this to happen. And this is an x plus 6 squared plus 4. So, cool. This problem has become a different looking denominator here. The denominator now looks like this: x plus 6 squared plus 4. And so now it looks like a u squared plus an a squared. A u squared plus an a squared is the same as an a squared plus a u squared, of course. So that's classic arctangent. There it is. One more, I can finish this. One more comment though. So I chose to kind of shove the 40 off to the side, add the 36, and subtract the 36, and I ended up here. Another way is, if you see that you need the 36, you kind of you call that a 36 plus 4, and you group the 36 over here. There's your completed square. There's your 4. I mean, there's a couple ways to accomplish that move. All right, cool. So to finish this, I think it's this, and I think the answer is 1 over a. The a is a 2, of course. Arctangent u over a. I think the u is x plus 6. I don't think there's anything interesting happening with the du. If you do let u equal x plus 6, the du is just a dx. So that's nice. So nobody's spitting out a 1/2 or a 1/8 or a 1. But something else, there is one other aspect to this problem. There's a 3 on top. And you pull the 3 out and you put it back, it's sitting right in front of this. So 3/2, if you want to say 3/2. 3/2 arctangent x plus 6 over 2. Cool. That's the answer. I want to erase it and do another one, please. Erase it and do another one here. Look at this one. This is all, I like to put some weird number on top. It doesn't really matter. You're allowed to pull it out front. And then I construct the problem like this. I'm going to try... I'm going to try a 6x minus x squared. Okay, so that sure looks a little different. Again, it doesn't fit, it's got the square root. It kind of reminds me of this, but that's got to be a constant. It can't have a variable x in there. I mean, it's not this. But if I complete the square, I think I can manipulate it into one of these forms, I think. So I go off to my scrap paper. I take this out of the square root, and I rewrite it as a negative x squared plus 6x. So that's it. There it is. And I try to complete the square. One thing I know about completing the square is you can never really complete the square when there's a coefficient on that x squared. So I'm going to factor out that negative sign. That leaves me x squared minus 6x. Okay, I need that negative sign sort of factored out. So, okay, now I can complete the square. I can add the right number here. It's Half of this is a 3, square it, it's a 9. I need to add a 9. That makes me have a perfect completed square. So usually, you know, you add a 9, you better come over here and subtract a 9. But wait a minute, time out. You know, I added this 9, but with this negative sign factored out, that's really a negative 9 I just added. That's a negative 9 I just put on there. So to compensate, I should do the opposite. I should add a 9 here. That added 9 is really a negative 9. I add a 9 to do the opposite. This is now a perfect completed square with a negative sign out front. It's x minus 3 squared with a negative sign out front. I actually want to reverse the way I write this. I want to write it as 9 minus x minus 3 squared. And that's this denominator. I mean, this is this. We started with this thing out of the square root, in the square root, and I worked on it, completed the square. So now let's put it back. This integral now becomes a 5 over the square root. The square root is there. And then it's this, 9 minus x minus 3 squared dx. This turned into this by completing the square. All right, cool. You know what? I think that looks like an a squared minus u squared. An a squared minus u squared. My a is a 3. My u is an x minus 3. It's arc sine. Arc sine doesn't have a 1 over a in front of it. So here comes the answer. Arc sine u over a. Wow. Plus c. U over a. That's right. That's right. And there's a 5 out front. Thank you very much. So that was fun. All right. Good luck. Do some homework. 5-8. Look for another assignment coming up. All right. Thank you.